So for Fresnel diffraction for a circular aperture, we have best focus, which will just be a central bright spot, and then we have defocus on either side, moving away from the best focus, and we'll see a single dark spot surrounded by a bright spot. And this corresponds to plus or minus 1 wave of defocus, which corresponds to plus or minus 2 for a Fresnel number. Our Fresnel number is calculated based on the size of our aperture, the wavelength of light, and this L factor. And the L factor is determined by this equation, Z1, Z2 over Z1 plus Z2. For our collimated light coming in, Z1 approaches infinity, which means that our L will be approximately equal to Z2.
So the MTF is a figure of merit for your optical system. It corresponds to how much resolution your optical system has. It means the ability to distinguish between 2 points. Right here is a picture of an MTF of an aberration-free system. Basically, when your optical system has very small aberrations, the only thing you're limited to is the effects of diffraction from your apertures. So the MTF is the modulus of the optical transfer function. Remember that the Fourier transform that creates the optical transform is a complex function, and taking the modulus gives you the MTF. The MTF has a cutoff frequency, which corresponds to what is the smallest spatial parameter your optical system can distinguish based off the Rayleigh criterion. So the MTF is the modulation of your image divided by the modulation of your object. And here's the equation that describes the curve, the plot that you just saw. The phase is equal to cosine inverse divided by lambda times the spatial frequency divided by 2NA. If you manipulate that equation, you'll see that lambda over 2NA is equal to lambda f number. So when your frequency is equal to 1 over lambda f number, your phase is equal to the cosine inverse of 1, which is 2 pi. Now, when dealing with a diffraction limited system, you have a spot size that's based off of your diffraction. Your spot size is basically 2.44 lambda f number, once again based off the Rayleigh criterion theorem.
Alright, so here we have the setup for our system. The first thing we did was check the alignment to make sure that everything was aligned, and in our case it wasn't, so we had to go through and realign our system to make sure that we were getting an image plane out of our microscope to make sure that we could do our measurements for this lab. Alright, so for the end of the lab, we tried to profile the LSF of our system. We used a slit and a power meter, and to do that, we wanted to measure it at best focus. To find best focus, we've first found a location of 1 wave of defocus and -1 wave of defocus, which occur when a dark spot first appears in the center of our Fresnel diffraction, and the average of those 2 locations will give us our best focus. So then we move the slit across the beam to profile the LSF at both these defocus locations for +1 wave defocus and -1 wave defocus, and finally the central position, which is the best focus.
Here's an example of how we found the best focus position. As you can see, as we begin to move through the rail, we begin to see fringes. We did this for an optical difference of 1 and -1 and averaged the 2 values. These are the results that we obtain when we move the slit through the beam. This is the location at best focus. As you can see, it looks exactly as we expect it to look, which is a Gaussian curve. Then we moved our location was about 1 lambda. As you can see, we get these 2 imperfections that we think we could have eliminated by taking more points, but you get a general shape of a Gaussian again. And then finally, we moved it to where the optical path difference was about 1 wave, and again, it looks like a Gaussian curve. Then we simulated our system by obtaining the prescription of our lens that we were using, and we simulated on Zmax, and we did the MTF plot, and it calculated a sampling frequency of about 11.7 line pairs per millimeter, and using the equations we previously discussed, we calculated 12 line pairs per millimeter, so the 2 values are relatively close. Then we did a MATLAB simulation with our data points that we obtained, and this is the MTF plot that we obtained for the best focus. And as you can see, the sampling frequency was about 12 line pairs per millimeter, which is what we expected it to be.